video here on triglycerides. So triglycerides are just a big fancy word for 3-glyceride, referring to glycerol. And glycerol is just this structure here. It's an alcohol, but as you can see, it's got 3 hydroxyl groups, which is where the tri comes from. You also react this structure of glycerol with 3 carboxylic acids, and when you do that, you form a triglyceride. So a triglyceride is a triester. They're fats and oils, and they're derived from plants and animals, depending on how many double bonds they have, so their degree of saturation or otherwise, that determines whether they're coming or originating from plants or animals. Triesters because they contain 3 functional groups, because they are created by the reaction of an alcohol containing 3 hydroxyl groups with 3 carboxylic acids. Now, this alcohol known as glycerol is also, if you named it systematically, propane 1,2,3-triol, 3 carbons on first, second, and third carbons is the hydroxyl group, so propane 1,2,3-triol. And you react that with 3 long straight chain carboxylic acids. So as you can see here, we've got these R dash, R double dash, and R triple dash, and that's signifying that they don't have to be the same carboxylic acid. The ester group will form, and then the R groups will be on the end. Now, this is a condensation reaction, like any esterification reaction, but in this case, we're forming 3 lots of water because we have 3 of the reactions taking place. Now, these carboxylic acids are often very, very long straight chains, and that is because, and so they're therefore known as fatty acids. They always contain an even number of carbon atoms, usually between 12 and 20, and that's just because of what they're formed from. The things that they're formed from only have even numbers because they're made up of 2 carbon length components. And so when you add lots of 2's together, you get even numbers. So they contain an even number, and they're unbranched. So they don't have any side chains. They're nice, consistent, long molecules. Now these acids, so they don't have alkyl groups, but they can have different levels of straightness or kinking, if you like. And that depends on their level of saturation, which is talking about how many double bonds they are. So if they're saturated, that means that they have no double bonds. If they're monounsaturated, that means they've got 1 double bond, and if they're or 1 triple bond. And if they're polyunsaturated, it means they've got many double or triple bonds. Now, this hydrocarbon chain, as we talked before, they often have between 12 and 20 carbons. So therefore, they have this long hydrogen carbon portion. That's the dominant structural feature of this molecule, and therefore they are insoluble in water. Now, as you can see here, we've got a triglyceride, and it's actually been formed by a reaction between a saturated fatty acid with no double bonds, with a monounsaturated fatty acid with 1 double bond, and with a polyunsaturated acid with 3 double bonds. Now, as I said before, the source of triglyceride actually depends on what they're on whether they're a solid or a liquid, and it determines whether they're a fat or an oil. So if they're from animals, they actually are solids, and they have a greater percent of saturated ones. So they have a greater percent of this sort of carbon chain. If they're from the land or fish or plants, they're often a liquid, and that's oil. So you could add in there all plants. And we think about that, if you think about canola oil and things like that, fish oil, they're oils, and they have a greater percent of unsaturated. So they've got a greater percent of this one or that one. Now, the reason that gives different properties is because if you've got lots and lots of these straight ones, they pack together really well. So they pack together really closely. They have very strong dispersion forces, and therefore they are more likely to be a solid. Whereas the more you get unsaturated, the higher the degree of unsaturation, the more you get kinks in the chain. And so therefore the weaker the bonds are, and therefore it forms more of a liquid. So if we have saturated fatty acids, they contain only single bonds, straight carbon chains. Therefore, they can pack together closely, increasing the dispersion forces. and therefore they have higher melting points and are solids. If you've got unsaturated, they contain at least one double or triple bond and have kinks. Everywhere there's a double bond, or a triple bond, they're going to have a kink. And therefore, because we've got kinky structures packing on top of each other with branches, they're going to pack together less closely, and the dispersion forces are not going to be as strong. They have lower melting points, therefore, and are liquids at room temperature. Now, naturally, as the length of the carbon chain increases, you're going to have a higher melting point as well. So if you've got a longer carbon chain, you're going to have a higher melting point. And this is just a really good schematic of what we're talking about. Here is a solid, hard fat. As you can see, straight chains beautifully stacked together, strong dispersion forces. Over here, we've got a double bond in here that is causing some kinking, and so therefore the chains are more spread apart. They can't pack as closely together, and therefore the weak dispersion forces originate, and you have an oil, a liquid. Now, we can actually quantitatively measure the degree of unsaturation, and that's measured by the number of double bonds that are present. So if we have any alkene, we should know this from before, we can add in group 7 elements. So we can add in bromine, we can add in iodine, we can add in chlorine, and we can add in hydrogen. When we add them in, we get this structure here. So we remove the double bond. As you can see, the double bond's gone, and we've replaced it with 2 bonds to 2 Br atoms. So when we add it on, it becomes bromo. If we added Cl, it becomes chloro. If we added iodine, it becomes iodo. If we add bromine, which is brown, as you can see here, can't see it on yours, but we able to see it here. When we add that over the double bond, so originally here, bromine is brown or orange. When we add it in, it becomes colorless because we've broken up that Br too. So that enables us to see what's going on. So if we add bromine to an unsaturated, which means it's got double bonds, we're going to have a loss of color. But if we add it to a saturated molecule, we're not going to have a loss of color because a saturated molecule doesn't have any double bonds, and therefore the bromine isn't going to add over the double bonds. So therefore we can quantitatively see the measure of the degree of unsaturation. If you've got, if we have to react a lot of bromine to this in order for it to go colorless, that would tell us, or add a lot of bromine to whatever structure, whatever fatty acid we're talking about, that would tell us that we've got a lot of Br, a lot of double bonds in our fatty acid. So again, let me repeat. If we have to add a lot of bromine into our structure, that would tell me I've got a lot of double bonds. Okay. If I only have to add a little bit in order for it to go colorless, I've got less double bonds or triple bonds. If I only have to add, if I add it and nothing happens, well then it's obviously going to be saturated. So we can actually measure, if we measure the mass that reacts, that will tell us the degree of unsaturation. Another specific way is to measure something called the iodine number. And that represents the mass that reacts with 100 grams of the triglyceride. If you have a higher value, you have a higher degree of unsaturation. If you have a higher iodine value, higher degree of unsaturation. Finally, we have hydrogenation. So hydrogenation is how we actually convert oils into fats by reducing unsaturation. So oils are going to go into fats if we can get rid of those double bonds. So hydrogenation, as the name suggests, is the process of adding in hydrogen. If we add in hydrogen across the double bonds, then we're going to remove those double bonds, and so therefore they're going to be able to pack together more closely, and we're going to be able to have more high melting point again. Now this is a very slow reaction, so we have high temperatures and pressure and an Ni catalyst, and it's needful to know the conditions of these reactions. Whilst we might not remove every single double bond, we are going to remove most of them, and so therefore you're going to have a solid happening at room temperature. Now, like esters, we can also hydrolyze triglycerides, and so we can break them up into their constituent molecules. We're going to, if we hydrolyze triglycerides, we're going to break them up in acidic conditions into the glycerol or the propane 1,2,3-triol and into 3 carboxylic acids. If we do it in alkaline solution, like esters, we will break it up into glycerol, but this time into the carboxylate ion, which has the negative charge. And if we had a sodium ion here, we'd be able to add a sodium ion here over here. Now we do require high temperature and we need concentrated solutions in order for this to occur. So either concentrated acid or concentrated alkali. Final thing we want to learn about is something quite cool. It's called Micelles. And we have, you might remember from last year, Micelles in ice cream, mayonnaise, a whole lot of things. Soap is often the most common example. So hydrolysis, if we break up these, we get these really long, in alkaline conditions, we get these carboxylate salts. Now remember, these are formed from really, really long chain acids. And so we get these structures which have really, really long nonpolar tails and a charged head group, an ionic charged head group because it's negatively charged. So we've got a really polar segment here and a really non-polar segment. Now this non-polar segment is hydrophobic, as we've got down here, whereas this is hydrophilic. In fact, we can do iron dipole bonding up here as well as hydrogen bonding with this oxygen. So we've got this generic structure of a hydrophobic tail and a hydrophilic head. These actually arrange themselves in order to form micelles. So if you imagine a whole heap of these, they arrange themselves a bit like this. So here is the nonpolar tail and here is the head. And so they arrange themselves around in solution with all these carboxylate ions, with the long nonpolar hydrocarbon chain and the anionic head, which is hydrophilic. So in aqueous solution, we form these core structures, these circular spherical structures, where we've got these anionic heads on the outside because they are water liveling. They are hydrophilic, they interact with iron dipole bonding and hydrogen bonding with water. And on the inside, we have the hydrophobic hydrocarbon portions, which do not want to be interacting with water. So we form a micelle. It's a nonpolar core with these hydrophobic hydrocarbon chains, and it's got a polar ionic surface with the hydrophilic ends or the head groups. Now the micelles repel each other naturally. If you think of this one compared to another micelle exactly like it, they've got negatively charged heads, so they're going to repel each other. And so if we've got grease, we can break up grease into small particles if we add in soap, and it forms micelles, because they will repel each other. And so they'll be broken up, and then the micelles, which are soluble in water, will be washed away. So if you imagine dirt, the hydrocarbon portion of the carboxylate salt would interact with the dirt because the dirt is hydrophobic, and so they'll interact. The micellar surface would interact with the water. And so we'd have several of these micelles forming, which would, one, repel each other, and then two, if we agitate it, we'll have the head, the outside of the head interacting with the water, so it's quite a strong interaction. And so if we agitate it, that we'll be able to break the interaction with the surface of whatever, the surface of the cloth, for example, and that will break the micelle off and carry the dirt away as well, because the dirt will be involved in the hydrophobic center. So then they can dissolve and move nonpolar substances, therefore, through a medium. So if we've got polymers and they've got this hydrophilic head and hydrophobic end, we can chuck a hydrophobic or nonpolar drug into the center of this micelle, and that can be carried around the body by this micelle, as the aqueous medium of blood would be able to interact with the surface of the polar micelle. Now this aqueous medium of blood wouldn't normally be able to transport nonpolar drugs. If we position the drug in the center of the micelle, we surround it with the hydrophobic end, so the hydrophobic center of the micelle surrounded by the hydrophobic end of the polymer. And then the hydrophilic ends of the polymer on the outside of the micelle will interact with the aqueous blood and will be able to transport it around. So we've got the hydrophobic drug interacting with the hydrophobic end of the molecule in the center, and then we've got the hydrophilic heads of the molecule interacting with water or with the aqueous medium of blood so that we can carry drugs around the body. Okay. That is micelles. And